So our raison d'etre is to find a lab. So our raison d'etre is to design a lab that can test. So our reason for existing is to design a lab that can. So in this video, we will design a lab that can test the law of conservation of mechanical energy.
If mechanical energy is conserved and we release a marble down the ramp of known height, then we can predict the velocity of the marble at the bottom.
So first we set up the marble chuck. Then we set up the photo gates at the bottom of the marble chuck. Then we measure the height of the beginning of the marble chuck.
Give me your phone. Give me your phone. Set up marble track. We then measure velocity of marble across 3 trials using photo gates. Number 5, we find the average of the velocities. Then we also check if the kinetic energy using the velocity matches the gravitational potential energy at the beginning of the trial.
The first thing we do is release the marble from the top of the marble track. Then as it moves, its x position continues to increase relative to its initial x position. Then the marble accelerates as it moves down the track. By placing 2 photo gates at the bottom of the track, we can measure the velocity when it reaches the end. With this data, we can measure the initial mechanical energy and compare it with the final mechanical energy, with a reference level being the top of the table.
So, to display this data, we can do it really simply. On one column, we have trials. On the other column, we have velocities. So, after performing 3 trial runs, as can be seen here,
You don't know how to catch a marble.
1.31 meters per second, 1.31 meters per second, and 1.35 meters per second, because our lab decided to suddenly spice it up at the end. So with this data, we can calculate the average. So our average is just our velocities over 3, because we did 3 trial runs. So we get an average of 1.32 meters per second. So given the speeds that we calculated, which once again are 1.31, 1.31, and 1.35, we can first set our initial mechanical energy equal to our final mechanical energy. So at the beginning, we had gravitational potential energy from the ramp. So we can say our initial mechanical energy is mgh. And then on the other side, we know that our marble, is literally moving as we go. And at our final point, it should have carried along most of the potential energy that it got from the beginning. So now we can say that the final mechanical energy is 1/2 mv squared, which is kinetic energy. So now we can disregard mass because mass is on both sides, so it cancels out. Now we have gh equals 1/2 v squared. 2gh equals v squared, and v equals the square root of 2 times gravity times height. So now that we know that height is 0.19 meters as we measured, and gravity, as we did not measure, is 9.81 meters per second squared. Plugging this into our original equation, we can get that the square root of 2 times 9.81 times 0.19 is equal to our velocity. So our calculated velocity is 1.98 meters per second. Now what we got instead is 1.32 meters per second on average. So now let's calculate our percent error. Our percent error, the formula for it itself, is just our experimental minus our theoretical over our theoretical times 100. So we plug in 1.32 meters per second minus 1.98 meters per second over 1.98 meters per second. So times 100 would get us 33.3% error. Exactly. So with such an error, can we even consider that mechanical energy really is conserved? Maybe they are lying to us. Maybe it's all just a fraud to. What even was the purpose of this lab? I'm so glad you asked. So our real purpose, or our raison d'etre, was to design a lab that can test the law of conservation of mechanical energy. And our hypothesis was that if mechanical energy is conserved, and we release a marble down a ramp of known height, then we can predict the velocity at the bottom.
We have made some assumptions in this lab, however. Notably, we're ignoring the existence of any air resistance or friction. We are also ignoring any possible rotational kinetic energy that may arise from the marble rolling down the ramp.
Sources of experimental uncertainty mainly arise Some sources of experimental uncertainty mainly arise from the assumptions we made before, specifically ignoring friction forces and any energy expended through rotational kinetic energy. We also had to deal with limited precision with our meter stick and our photo gates, which we are not able to measure the instantaneous velocity.
Our hypothesis was supported because our gravitational potential energy is at the top is roughly similar to the kinetic energy at the bottom. A 33% discrepancy can be identified, but that's due to rotational kinetic energy and friction that we assume to be negligible. Insert funny joke.
Here's my ID.
Okay, thank you.
Oh no! I dropped my ID. I wonder how much energy was in that
He's
drop.
now
Do you
illegal.
wonder how
He
much
doesn't have an
energy
ID. He's immigrant. Wait, are we doing improv? What are we doing?